In this video, we'll be looking at Chapter 15, Section I.2 on the angle between two lines. Remember the dot product or the scalar product from our previous video. Remember also that we did some examples where we rearranged this equation to solve for theta. And we can do that so that it looks like this. Now we can use this equation to help us find the angle between any two lines. So let's say we have two lines which again stretch into to forever, and we'll call this line 1 and we'll call this line 2. Well, lines aren't vectors, but we can come up with what we call direction vectors for each line. We'll call this first direction vector, vector A, and the second direction vector, vector B. So if we know these direction vectors, we can use the equation here, this version of the dot product, to help us find angle theta. And in this case, we want theta to always be the acute angle. So notice that there are two different angles that we could find between any two lines that intersect. One will be less than 90, and that's the one that we want to find, and one will be greater than 90. And really, it's just by convention that we want to find the acute angle. Mathematicians have gotten together and said, all right, when we do this, we'll be talking about the acute angle and not the obtuse angle. So remember to always find the smaller of the two angles. Now the direction vectors we have to get from the equations for the lines. So if I have an equation for a line in this form, y equals mx plus b, right? Remember that the m here is the slope of the line, or the gradient as your textbook calls it. Now if we know the slope, we can find the direction vector, and it's probably easiest to give you an actual example here. If the slope of a line is 2/3, then the direction vector for that line is equal to 3/2. And that's because the gradient, or the slope, remember, has the rise or the y movement first, and then the run or the x change second on the bottom. And so if this is the y, then we need to put that in the y component of our direction vector. And if this is the x change, we need to put that in the x component of our direction vector. To put it in slightly more general terms, if we have a slope that equals a over b, then the direction vector is equal to b over a. And we'll do a few examples to show you how this works. In this example problem, we're asked to find the angle between two lines with these equations. So the first thing that we need to do is find the slope of each of these equations. We'll call this equation A, and we're going to rearrange the first equation here to get it in the form y equals mx plus b. And so I'm going to subtract 2x from both sides to rearrange that equation. And therefore my slope is -2, or -2/1. Therefore the direction vector for this line is equal to 1/-2. Okay, and for line B, we'll do a little bit of an adjustment here. Let's use green, and we'll bring 2x again over, so we have -3y equals -2x plus 18. Then I need to divide by -3, so I have y equals 2/3 x minus 6. And the direction vector, therefore, is 3 over 2, because my slope is 2 over 3. Now in the case of the first equation, you'll notice that we had a negative slope, and so some people might ask, well, should it be negative 1 over positive 2 or positive 1 over negative 2? And it actually doesn't matter. They will both get you the same results in the end. By convention, I think we put the negative in the bottom with the y component, but I don't think it really matters. You can do either. Now that we have our direction vectors, we can use our rearranged dot product, which is cosine theta equals a1 times b1 plus a2 times b2 over the magnitude of vector A times the magnitude of vector B, and we just need to plug in some numbers now. So A1 is 1, B1 is 3, A2 is negative 2, and B2 is 2. And remember the magnitude of vector A is the square root of the sum of both components squared, so 1 squared plus negative 2 squared, and over here I have the square root of 3 squared plus 2 squared. We do a little simplification here, and we have 4 I'm sorry, that would be 3. So 3 minus 4 over the square root of 5 times the square root of 13. So we have negative 1 over the square root of 65. And this equals cosine theta. So to find theta, I take the inverse cosine, making sure my calculator's in degrees, of negative 1 over the square root of 65. And this equals 97.1 degrees. But hopefully you notice that this number, this angle, is greater than 90 degrees. So it's not an acute angle. It's not the acute angle between these two lines. So if I have these two lines, I just found the obtuse angle. So to find the true theta, I need to subtract 97.1 from 180, and that's going to get me 82.9 degrees. And this is the acute angle. So remember to always find the acute angle. Now, one thing that your textbook does, if you're looking at your textbook, back up here in the modified dot product equation, your textbook puts absolute values around the numerator. So we're really finding the absolute value of the arithmetic form of the dot product. And so if we followed that through, we'd be taking the absolute value here, here, and here, and that would get us a positive 1. And what that would do when we plug the inverse cosine of positive 1 over square root of 65, that would bring us right to the answer here. You have to remember to put that absolute value sign only when you're finding the acute angle between two intersecting lines. I prefer to just use the dot product as is, rearrange it as needed, and then remember to find the acute angle at the end. But either way will work, and it's really a matter of preference for you.